Welcome to Lecture 2.9, Russell's Paradox and the Halting Problem. Let's first recall Russell's paradox from the beginning of this course. That said, suppose a town's barber shaves every man who doesn't shave himself. Who shaves the barber? This paradox is due to British philosopher, logician, and mathematician Bertrand Russell, born in 1872, died in 1970, as an informal way to describe a more mathematical paradox, which is, consider the set of all sets that don't contain themselves. Formally, if such a set existed, we could write it as S equals the set of all A, where A is the set, but A is not an element of itself. It certainly seems harmless, but let's see what goes wrong with it. If such a set exists, then we can ask, does it or does it not contain itself? Well, there's two cases. The first one is that S contains itself. In other words, S is an element of S. Then by definition of S, all sets that do not contain themselves, well, S cannot be an element in S. So this by itself is not a contradiction, but we can eliminate the case that S contains itself, so S must not contain itself. And that's the second case. But if S does not contain itself, then by definition of S, S has to contain itself. And together, this is a contradiction, because S cannot contain itself and not contain itself. So this is the more mathematical version of Russell's paradox, and the little story about the barber is sort of how he described it to the masses. Now I'll show you a fix for Russell's paradox, though it might be a little bit unsatisfying because it almost seems like it's cheating, but it's not. So let's go back to the idea of sets. We said let's imagine the collection of all possible sets. That's okay. When I use the word collection, I'm abstractly thinking of all possible sets. I can't say that that is actually a set itself. We saw how that resulted in a paradox, but I can still say the collection of all sets. That's okay. So I'm going to define this concept to be I'm going to call this a universal set. What I just said it was collection, but formally mathematicians will call this a universal set. Not actually a set, even though it actually contains the word set, and we'll denote it by U. So this will contain all sets. So S is going to be the set of all things A, sets A, that are contained in U and do not contain themselves. Recall what we had before. So before, instead of this condition A being in the universal set, we said A is a set. And A does not contain itself. Now we're making one slight change. We're dropping the requirement that A is a set and just saying that A lives in our universe. As we did before, we can ask, does S contain itself? And as before, there are two cases. Either it does or it doesn't. In the first case, suppose that it contains itself. So S is an element of S. Then by definition, these two conditions hold. In other words, S is an element of the universal set U, and S does not contain itself. And that last condition is in contradiction with the assumption that S does contain itself. And so we conclude that this case is impossible. So this set of all sets that do not contain themselves cannot contain itself. Let's now consider the other possibility, that S is not an element of itself. So in Russell's paradox, we concluded that this implied that S contained itself, which is impossible. So both of these cases cannot happen, which is the paradox. we will not reach the same conclusion here. Let's see why. So if S is not an element of S, that means that these two conditions cannot both hold. In other words, it is not true that S is contained in U and S is not an element of itself. So by De Morgan's law, the negation of a conjunction, the negation of, let's call this A and B, is not A or not B. In other words, the negation of S being contained in U is that S is not in U. The negation of S not being an element of itself is that S is contained in itself. So in other words, if S does not contain itself, then one of these two things has to be true. Either S is in itself, which just by itself would be the contradiction that we got in the previous slide, but we have a backdoor now. We have another possibility. Maybe S just isn't an element of the universal set. And that's what we say. S is not contained in U. So U is the universe of all sets, and this thing S, this does exist, but it's just not in the same universe. It's in something bigger. In other words, there cannot exist a set of all sets, but we can define the collection of all sets, or some people call it the class of all sets. That is still an object, but it just lives in a bigger universe. Remember, I said this would seem like I'm cheating, but it is legit. One may ask whether we can always get rid of contradictions in this manner. In other words, can we ever increase our universe big enough so that we never have any contradictions left? In 1931, Kurt Gödel said no. He proved something that is now known as the Incompleteness Theorem, and I will not state this formally because it is very technical and has a lot of set theory jargon, but informally is all that you basically need to get the picture. He said that every axiomatic system that is sufficient enough to develop the basic laws of arithmetic cannot be both consistent and complete. In other words, there will always be either paradoxes or statements that are unprovable. That means that they are outside of the laws of logic. They are neither true nor false, which is a really weird thing if you sit down and try to wrap your head around it. And now we come to the second part of the title of this lecture, which is the halting problem. Alan Turing, born in 1912, died in 1954, was one of the pioneers of the field of computer science. It's not clear when the first computer was built because it's not clear how to define what a computer is, but I think a consensus on Google tells me that it was done by Charles Babbage in the late 1800s. But Alan Turing is often called the father of theoretical computer science because of the halting problem. He did a lot more than just theoretical computer science. In fact, during World War II, he decrypted German intelligence codes for the British government, which played a major role in the Allies defeating the Nazis. This was made into a wonderful movie you've likely heard of called The Imitation Game in the year 2014, and I highly recommend that you go watch it. One of Turing's many contributions to computer science is the formalization of the algorithm. And he basically did this before computers existed. Though there had been, as I said, a few isolated people who had invented something that could be called a computer, it's not like anyone actually had one in practice. So everything that Turing did was theoretical. If we had one of these computational machines, what could it do? And what were its limitations? And that's a remarkable achievement given that these things didn't really exist. There are people in modern times, though, who do similar things with quantum computers. Now, a quantum computer is somehow a much more improved version of a computer. Instead of using binary bits, 0 and 1, it uses quantum bits, which are superpositions and entanglements of regular bits that uses quantum mechanical theory, which I don't really understand much at all. But all I know is that somehow, if these quantum computers could exist, they could solve problems that our regular computers could not. Or at least it will take the life of the universe to solve. So things that are NP complete or NP hard, a quantum computer could solve in a matter of seconds. Now we can build a quantum computer, but only with a very few qubits. So it's of no practical use. But if we could build a quantum computer that is large enough, then it would destroy our entire crypto systems. So that said, a lot of government agencies, I know the United States, the National Security Agency, is pouring a ton of money into research for people who want to study quantum cryptography. Now you could say that this is for fun, but I think more realistically, there's people who are actually concerned that the reality of a high-powered quantum computer is closer than we think. I personally don't think it'll be in any of our lifetimes, but they are throwing a lot of money in it. So there are people who know a lot more than me who are concerned, even if just a little bit. And most of this stuff is highly classified anyway, so we'll probably never know how realistic it is. Okay, so moving on. Alan Turing in the 1930s proved that the halting problem was unprovable. And to motivate this, let me actually go to modern times. Most of us have probably written at least a very basic computer program, so we know what it's like for a program to loop forever, either intentionally or accidentally. Usually it's accidentally, not something that we want to happen. Because of that, it would be really nice if there existed some sort of product that we could buy that could check our program in advance and say, yes or no, that program will definitely loop forever or definitely halt. That would be worth a lot of money if it existed. And Alan Turing proved that such a program is impossible to build. The question of whether a computer program will halt or loop forever is unprovable. Formally, he showed that there cannot exist a computer algorithm that accepts any algorithm X as input and any data set D. So think of this as the computer program X and D as the input to the program, like the parameters. And the algorithm will output halts if X halts with input D, and it outputs loops forever if X loops forever with input D. So in other words, there cannot be a program that checks whether some computer program halts. And this is remarkable that he did this in the 1930s, because I'm sure this is before he ever programmed a computer and ran into things like infinite loops. All of this was purely theoretical. It's a natural question to ask in the 1980s or 1990s, but not in the 1930s. He was way ahead of his time. Turing proved this by contradiction, which shows you how powerful this method of proof can be. And I'm going to actually show you the proof. To summarize the method, he supposed that there existed such a halting checker algorithm, and he showed that if there does exist one, that it leads to an instance of Russell's paradox. In other words, a contradiction. Let's get started with Turing's proof of the halting problem. So here's the theorem, just restated. And remember that Turing proved this by contradiction. He said, suppose that there exists such an algorithm. And we'll call it check halt, and it takes as an input the program x and the input data d. If x terminates in finitely many steps given d, then this program must print the word halts. Otherwise, it prints loops forever, and that's it. Okay, so where is the contradiction? Pause this lecture if you want to think about it for a minute or two. How are we going to somehow cook up an instance of Russell's paradox from just this? You see it? Okay, here's a hint. Consider what happens if we run check halt on a program X with itself as input. Obviously, for many programs, this would not even make sense, but consider this in general. I will use this to define an algorithm that I will call Russell, which takes as input some program X, which is just a string of text. So Russell is defined as follows. If running check halt with input X and data set X prints halt, then I will force the program to loop forever. So one way to do that is to just define a while loop and write 1, which is always true, so this thing will just loop forever. There's other ways to define infinite loops. This is probably the easiest one. Okay, so if check halt with input X and itself prints halts, then our program Russell will run forever. The other possibility is that if check halt with input X and X prints loops forever, then we just exit the program immediately. So we force it to halt. Okay, so what good does this do? We have a program that runs check halt on an arbitrary program and itself as input, and it does the opposite of what the output is. Do you see it? Take a moment to pause the lecture if you don't and see if you can figure it out. But don't feel bad if you don't. It's a really clever logical trick. What happens if you take this program Russell, which I have explicitly written out the pseudocode for, though the existence absolutely depends on the existence of check halt, and we take this program and we input itself into the program. We run it on itself. Think about what happens. This is where we are going to run into Russell's paradox. Let's see why. Okay, let's go through in detail what happens when we run the program Russell with the program Russell as input. Now, this is the kind of thing that for whatever reason, you're probably going to have to pause the video multiple times to wrap your head around each step of the process. It's just the nature of the beast. I have to do the same thing every time I go through it myself as well. I don't know why. So don't feel bad. You're not alone. Okay, case 1. Russell of Russell terminates after finitely many steps. Think about what that means. If this terminates, then check halt with inputs Russell and Russell prints halts, because that's what check halt does. It inputs the program Russell and the data input Russell and says, does it halt or does it loop forever? And if it terminates, it prints halts. However, by construction of Russell, this means that the program Russell with input Russell loops forever. By construction, it gets stuck in that while one loop. Case 2 is that Russell of Russell loops forever. In this case, check halt will report that. It will print loops forever, but by construction of the program Russell, it will halt. Remember, that's where we ended the program anytime that we saw this as output. This is a contradiction, and it means that the check halt algorithm cannot exist. That was the only theoretical part of this. Now, we wrote actual pseudocode for Russell, what it does. But for check halt, we just said, let's suppose that this mysterious program existed. And let's go back and see, why is this a contradiction? Well, if Russell of Russell terminates after finally many steps, then by construction, how we set it up, it actually must loop forever, which is impossible. So that means the other case must be true. Russell of Russell loops forever, but that is also impossible because by construction, that means that Russell of Russell must halt. So neither of these cases are possible, so such a program cannot exist, and such a program, the only reason we thought it could exist is because we assumed that check halt existed. So there is our contradiction. The halting problem is said to be undecidable. It requires a yes or no answer, but there cannot exist any algorithm to answer it for all inputs. And that's key, because for really simple programs, it's actually easy to check whether or not it halts or not. It's just not possible to check it for any complicated program that you could write. And that is a purely theoretical proof that Alan Turing did in the 1930s before computers were really in existence. I think that is an incredible achievement. Since Turing's proof of the halting problem, there have been many other problems in mathematics that have been shown to be undecidable. And I don't know the details about most of these, but I know that a lot of these, the proof goes by assuming that these problems could be solved and showing that that will actually solve the halting problem. And that is the contradiction. So I'm going to give you a list of some of these problems. If you don't know the topic, that's perfectly fine. This is just for anyone who is interested. It's the tip of the iceberg. You can start Googling these on your own if you want. Our first example is from abstract algebra. And the question is to determine whether or not two groups are isomorphic. So you don't need to know what a group is or what isomorphic means. Isomorphic just means they have the same structure informally. And a group informally is a set with a binary operation, something like addition or multiplication or function composition. For example, consider the group consisting of I, the complex, so I, the square root of negative 1, I squared is negative 1, I cubed is negative I, and I to the fourth is 1. And then if you keep multiplying by I, you cycle back here. So this is a group, it's a set with the operation multiplication. And one way we can write this abstractly, let me call this G1, is it's generated by some element x, turns out x equals I, with the property that x to the fourth equals 1. So this is an abstract way to write this group. So in general, if we have groups G1, well now I'm going to reuse G1, say generated by elements G1 up to Gn, subject to relations R1 up to Rm. So here a relation is a word in the generators that equals the identity element, in this case 1. So suppose you have a group like this and you have a group G2, which is generated by some other collection of G. So let me call these primes. So suppose you have another abstract group generated by K things, subject to relations R1 prime up to Rm prime. You can ask, are these things the same? And the symbol for this is this isomorphic symbol. So given two abstract sets like this with finitely many generators and finitely many relations, do they have the same structure? That question is undecidable. For many classes of groups, we can answer it. But in general, if we could answer that question, we could actually solve the halting problem. And that's how it was proven. Our next example is from the field of topology, which is basically the shape of things. For example, if you look at two-dimensional surfaces, like we live on a sphere, but how do you know that we don't live on a donut, which is a fundamentally different shape object, or a two-hole donut? These are called a torus. Now, on a sphere, we need only 4 colors to color in a map. So adjacent countries do not share the same country. But on a donut or a torus, we would actually need 7. And on a two-hole torus, I think we would need more. So this is basically the classification of two-dimensional surfaces, sphere or donuts, orientable surfaces. And the classification of three-dimensional surfaces is a lot more complicated. And there's a whole bunch of cases, and I think it was done a little bit after the turn of the century. And now, if you think about it, our universe is a three-dimensional surface. Which one is it? Is it the three-dimensional version of a sphere? Is it a three-dimensional version of a donut? Or is it one of the more complicated ones that doesn't exist in 2 dimensions? Okay, so what about 4 dimensions? That is actually the undecidable problem. Determine whether 2 4-dimensional topological spaces, just think surfaces, are homeomorphic. Are they actually the same? And homeomorphic, loosely speaking, means have the same structure. So this donut here is homeomorphic to this donut right here, because you can deform one into the other, even though that geometrically they look different. So the reason why this is impossible is because every topological space has an actual group, which is a group of paths. So this I'm probably going to be going over a lot of listeners, and that's okay. This is just for those who are interested. Don't worry if you don't follow all of this. So you can pick any point on a surface, and you can look at the set of all paths up to equivalence. And so I'm going to say one path goes around the hole, and another path goes around the arm like this. And then every path that starts and ends at this point on the sphere is going to be some number of cycles around the hole and some number of cycles around the arm. And so maybe you go around this 3 times and this 2 times, or this 8 times and this -4 times. So notice that on the sphere, no matter how you do any sort of path, since there's no holes, I'm trying to, sorry about my drawings, stay on the sphere, you can always deform this thing. You can contract it to just the path where you stand still. So all of the paths are equivalent on the sphere, but on the torus, depends on how many times you go around the hole or the arm. And this determines a group. But there's only some number of, it determines a group because you can multiply 2 paths together by doing them back to back. So if I do the red path and then the blue path, I get a more complicated path that goes this way and that way. So for 2-dimensional surfaces, there's only a very small collection of the possible groups that you can get in this manner, because there's only a very few number of surfaces. And even in 3 dimensions, there's a lot more groups you can get, but there's only so many. However, 4 dimensions is huge. It turns out that given any group, you can actually build a topological space. You can build a four-dimensional surface whose path group, this is called the fundamental group of the surface, is that group. So in other words, if you want to know whether G1 is isomorphic to G2 for two abstract groups, what you can do is build two four-dimensional surfaces. So these are 4D dimensional surfaces. And if you could conclusively determine whether these two surfaces are homeomorphic, have the same structure, then that would answer the question as to whether these two groups have the same structure. So answering this question for topological spaces, four-dimensional spaces, answering this question would answer an unprovable or undecidable question about groups, and we know that answering that would answer an undecidable problem, that is, the halting problem. Therefore, it is impossible to classify four-dimensional surfaces. I think that's a really neat result. This is abstract, geometric, topological question, has roots going back to the 1930s and Alan Turing studying theoretical computer science before the invention of the modern computer. Our next example comes from number theory. Determine whether a Diophantine equation has a solution over the integers. Think of this just as a multivariate polynomial like x to the 10th plus y to the 10th equals z to the 10th. Do there exist integer solutions to this outside of the trivial ones like 0, 0, 0? Now this is an undecidable problem in general. This is actually known. This is the answer to this one is no by Fermat's last theorem, but there are more complicated ones that we don't know. Now the answer to these, this is a yes or no question. It seems like the answer should be yes or no. And in some senses, it is. If there's a God out there, then God probably knows the answer to this question. But as humans, all we can do is check every single case. But there's infinitely many cases. We can never check all of the cases. And there is no logical reason that will ever lead us to the answer of true or false, yes or no. So to us, we say this is undecidable. It is not true nor false. But to a God, it might be true or it might be false. So here it's a little bit unclear, it's a little bit ambiguous as to what we mean by true versus false. True could be true, but not provable, or it could be actually true and provable. In linear algebra, more of you are probably familiar with this. If you have a finite set of n by n matrices with integer coefficients, you can ask, can they be multiplied to yield the zero matrix? Seems like a simple question, right? But you don't know how many multiplications it might take. Maybe you can do it, but it takes 2 billion multiplications of the matrices in some order. That question is undecidable. Next, in computational linguistics, determine whether two context-free grammars generate the same set of strings. I'm going to let you do your own research and Google what these things are. But it's basically a way to generate a language which was invented by Noam Chomsky, or at least he pioneered it, I think in about the 1950s, to study the basic structure underlying all languages, and it has since been used to study DNA sequences because those are basically a language that has some underlying structure. These are not random sequences. So it's a really fun topic. I encourage you to Google it and explore. And then our last one, coming full circle to the field of computer science again, is determine the Kolmogorov complexity of a string. This also has a complicated definition, but what you should think of is how much information you need to store a string. Like if you were going to run like WinZip on a string, how much space would it need? So for example, a string like 0, 1, 0, 1, 0, 1, 0, 1 repeated 100 times, it's going to have a very low complexity. You basically just need to store 2 bits. Whereas a random string of zeros and ones that really is random is going to have a much higher complexity. This you can compress into just a few bits of memory. If you were to put this into like WinZip or some other file compression program, this one, if everything truly is random, you can't compress it at all. One more thing that I want to leave you with is that many classic unsolved problems in mathematics may very well be unprovable, such as P versus NP, the Riemann hypothesis, the 3n plus 1 problem, and the Goldbach conjecture. So this first problem is out of computer science, and it asks whether or not really hard algorithms that are in the class, that are in the so-called NP class, can be solved simply using in polynomial time. It's more complicated than that, but I'm just summarizing it. The Riemann hypothesis is a famous problem, probably the most famous problem in number theory, which remains unsolved. There are some famous mathematicians that said if they were transported 500 years into the future, the first thing that they would ask is, has the Riemann hypothesis been proven? I think I would ask if we have been contacted by aliens, but that's just me. The 3n plus 1 problem, this is a really fun problem. It's really simple to state. If you have so you start with an integer, let's say 10, and if it's even, you divide by 2, so you get 5. If it's odd, well, you can't divide by 2 and get an integer, so you multiply by 3 and you add 1. So 5 times 3 is 15, plus 1 is 16. So now 16 you divide by 2, you get 8. Divide by 2, you get 4. You divide by 2, you get 2. You divide by 2, you get 1. And as far as we know, every single number that we start with eventually ends up at 1. And I think it was Paul Erdős that said, we have no idea why modern mathematics is not ready for this problem. We have absolutely no clue as to why. If you Google 3n plus 1 problem, Google image search, you'll see tons of pretty pictures of patterns of if you plot on the xy plane how many steps it takes to get down to 1. That is also both very random, but also both has random or has seemingly non-random pictures behind it. We have no idea how to prove this, and you can modify this problem to change the 3 into 1 to other numbers, and it has been shown that there are variants of this problem that are undecidable, but we don't know which ones. So very likely, I personally think that this is an undecidable problem. So this is one that a so-called, a God knows the answer to. He or she or it will know whether this is true or false, but with our mathematical logic, the answer to this very likely is completely independent of mathematics. There's no way we could ever prove whether it's true or false, nor can we check infinitely many cases. Finally, the Goldbach conjecture. This is a famous problem in number theory. It's very easy to state. It says every even number is the sum of 2 primes. For example, let's take 14, which is equal to 7 plus 7. 16 is equal to 5 plus 11. And this is something that we have checked for, I don't know, millions, billions, or numbers that are millions, billions, trillions of digits. Well, actually, I don't know how big. I know we have checked huge numbers into the millions, billions, and trillions. But we have no idea whether or not it is true. And there is a very good chance that this also is one of those things that is true. Well, I should say, if it's false, there will be a smallest counterexample. If it's false, we can come up with a no certificate. We will likely, or we will maybe eventually find a number and say, this is false, here is our counterexample. We can check it by exhaustive search. However, that smallest example might have 2 billion raised to the 2 billionth. It may have so many zeros. It may have 10 to the 10 to the 10 to the 10 to the 10 zeros that we will never find it. Now, there are probably math problems out there whose smallest counterexamples are 10 to the 10 to the 10 to the 10 to billions and billions of zeros. We will never find them. This might be one of them. But we suspect that it also might be true. And if it's true, there's a chance that we could prove it, but there's also a chance that it is unprovable. It is there. We would have to check infinitely many things. So a God would know, we would not. And so to a God, that statement would be true. To us, we say, I think it still is true. But technically, logically, we have to say it's not true or false. It is, just like the halting problem, undecidable. So I encourage you to go back and Google some of these things. Hopefully you enjoyed some of these fun topics. I think it's a really neat question, and it's fun to think about. Okay, so at this point, I don't actually know what topic we're going to do next, but I hope that you still stay with us. See you next time.